I'm based in Ann Arbor, Michigan. Go Blue, and I'm happy to be here with you all. So, agenda today. Um, oops, you know what? My screen skipped a slide, so I read through this, but you didn't see it. But that's the About Me slide. And then for the agenda that I'm going to cover today is really understanding the fundamentals of text-to-SQL solutions that are LLM backed. So this would be OpenAI or meta models, anything that's really using large language models for that SQL generation. And I'll talk a little bit about the history of that, but I think the LLM-based solutions are, certainly the ones that are getting the most use these days. I'm also going to talk about how really customizing text to SQL to your own data model. So this I think is very critical in this topic area. LLMs can generate SQL, but what we really want them to do is generate the SQL that's relevant to our own schemas, our own databases, and our own use cases. So I'm really going to kind of spend most of my time on that and really covering like how do you actually do that and get the best results and accuracy and performance out of these kinds of systems. And then finally, I'll demonstrate a solution. So there's some explanatory, but we'll actually kind of dive in and use one of these systems and see how it works and really see what the performance is and take what we talked about with the customization and make that real and look and see what that actually does in real life. So with that, if anyone has any questions initially, feel free to use the chat or to speak, and I'll be happy to pause at any time and cover more. So text to SQL, just as an introductory, I mean, it is what it sounds like. It's all about sort of translating natural language questions into, and this is important, valid and accurate SQL dialect. I put translating in double quotes because a lot of this is going to be about like, well, what does that really mean with an LLM? Because LLMs don't really understand what we're asking them to do. They're just prediction engines. So, and that's really important in this presentation is to understand that LLMs are really good at predicting things, but we have to give it enough knowledge or grounding data in order for it to predict what we want. So the thrust of the presentation is how do we do that? The text to SQL or natural language to SQL, I guess would be the better way to put it, has been around for like 60 years now. Ever since SQL existed, people wanted machines to write it for them. So that's kind of natural. But the success rate has been pretty limited in the past. I've used some old systems in the past and they never seem to work quite right. And what we're finding with large language models, like ChatGPT, which is built on top of the OpenAI models of GPT 3.5 and 4 and now 4.0, is that these models are really pretty good at generating SQL from natural language. And I think the reason for that is because large language models are, again, they're predictors. They predict what the likely best word is going to be or the next phrase is going to be based on some input. And for those that use SQL, well, SQL is kind of predictable. You have questions about data, and then SQL comes out and it does joins and where clause and so on. So it's kind of a predictable area. And it turns out LLMs are actually pretty good at this. But there are some limitations to it and provisos and things we have to do to get it to really be accurate. And that's what we'll be talking about tonight. So just to kind of what's an example of what we're talking about, text to SQL, we might start with a end user question. So what is the sum of sales for yellow bikes in London? So the sample data set I'm going to use is one of the AdventureWorks variants. So if you've been using Microsoft technologies for a while, you're probably kind of familiar with that database. So this is a question a user might ask. And in an ideal solution, we would send that to an LLM. Like ChatGPT is a front end on top of an LLM, but we might send it to GPT-4, or we might send it to Llama 3, or Phi 3, or some whatever model, and we would get back ideally something like this, right? So if we were giving this to a human operator, they probably do a pretty good job of coming up with this if they were good at SQL, they understood the schema, they understood what's in the database, and what does yellow mean and so on. So a human operator is going to do a pretty good job with this. But if a human operator didn't know about the schema, they probably wouldn't do a great job. And really, we have the same set of challenges with LLMs. We need to inform them how to do this correctly. So this result is actually correct for the sales LT schema in one of the VentureWorks databases. So it selects sum of line item totals, total sales, from say V sales is a view I created, and where the product color is yellow, product category spikes, customer city is London, makes sense. But there are some challenges with this, and this is, these are the challenges that we need to solve in order to get that great result that we saw on the previous slide. The first challenge is the LLMs usually aren't trained on your data model or our data model. So on LLMs, typically when OpenAI or Meta or Microsoft, when they trained their LLM, most of the big ones trained it on a lot of SQL. So they're pretty good at creating ANSI compatible SQL queries. The problem is the queries that they were trained on were somebody else's database. So how is that model going to predict the correct query for your database that you designed yourself and deployed in your organization? And the answer is probably not. Actually going to do a great job because without the knowledge of what the target schema is, most LMs, and if you've ever tried this, they'll just guess what the table names are and they'll guess what the column names are, and they will usually, like if it's a good model, it'll generate ANSI compatible SQL, but will it be usable? Usually out of the box, no. We usually need to do some training and some tuning in order to get it to work. So, and then the kind of the last challenge is users don't usually provide schema knowledge in their questions. So in the question we had where, what are the sales of yellow bikes in London, the user didn't say what is the total line item sum of, products with category bikes with they didn't name all those columns. They're not going to do that. They don't want to do it. If they have to do all that, they might as well write the SQL themselves. So we have to sort of solve these challenges in order to end up with a really good solution. And just kind of put a point on that, what is the problem that we kind of run into? We have our input query or question, and then we have our output target query that we actually want. And we have some problems here because, the LLM will recognize that sales is some kind of a column, but it won't know what table it's in. And it will recognize that it sees yellow bikes, but it doesn't know what that means. Well, is a yellow bike the thing they're looking for, or are they looking for bikes with another attribute that's yellow? And you can kind of think if you're, think like an LLM, you don't know. You're seeing all these things. You can kind of see that this turns into SQL, but you really don't have the details to do the thing that's in the lower right corner. So London, where is that? So the answer is model training or model tuning. It depends on it's some of it can be training, some of it can be tuning, some of it can be prompt engineering. So I'm going to sort of talk about like what are the things we can do, and I'm just going to call them generally model training. In other words, transferring our knowledge of the schema, the database content, and the structure of things to the large language models so that it can make the right prediction about the right answer given the question that we give it in natural language. So and just another example, just something to think about. If we take that same question again, this is if you just took that question and you put it in ChatGPT or some other large language model. I'm calling that like a naive LLM. It doesn't have any knowledge of the schema or the database contents or anything. This is about what you would get. You get something very similar to this. You can see it says select sum of sales as total sales from, and so on. Is that a valid ANSI SQL? Yeah, absolutely it is. That's completely valid, and it would not really pass a syntax check with any problems. The problem is that none of those tables and columns actually exist in the AdventureWorks database. There is no sales column. There is no table called sales table. The product is actually a table name, not a column name. So none of that would actually work. What we're really going for is the one below. So it has, more or less the same structure, but it's actually correct. So it picked up that product color has the color and customer city has the city, and so on. So there are some strategies that we can use to get from the naive LLM that doesn't know anything about our data to actually producing the right result for us. And there are 3 of them that I'm going to talk about. 2 of them we're actually going to use in the demo. But these are the ones, there are other techniques as well, but I think these are the ones that if you're not really familiar with this these are things to know about. So prompt engineering is one, which probably is a term many people have heard. What is prompt engineering? It's really kind of a $5 word for something, a concept that's not that difficult to understand. So prompt engineering mostly is about adding the right instructions to the prompt. So the prompt is the text question, the full text that we send to the LLM. And what we want to do is add instructions to the prompt to inform it about schema. In our case, for text-to-SQL, we're going to say, here's the schema that we're using. Here are some rules that we want you to follow. And this, the level of effort, pretty low. Really, all we're doing is writing text into the prompt to give additional instructions. It's not unlike if you were telling someone to go to do a task for you and you give them some additional information, on the way, turn left and then pick this up and make sure to do this. It's pretty much what prompt engineering is. And in this text-to-SQL use case, it's I'll show you some examples of it, but it's just kind of rules that we put in for the generation and maybe some metadata that we would put into the prompt through prompt engineering. The effectiveness is moderate. It's really good. I would probably say that there's very few LLM solutions that you would ever do that you wouldn't do any prompt engineering. You're always going to do some, but it's not necessarily going to solve every problem that we run into, particularly with this text-to-SQL sort of application. So the second technique to really kind of know about, and you may have heard of this one as well, it's retrieval augmented generation. Everybody calls it RAG because those three words don't roll off the tongue. But what RAG is really all about, it's kind of stated right in it. So we want to generate something from an LLM, but we're going to augment the instructions with retrieval, meaning that we're not going to statically type in something in the prompt, as prompt engineering generally does. We're going to dynamically go out and get some information that's relevant to the question at hand and put that in the prompt and send that to the LLM. Effort is kind of moderate. And the reason for moderate is it usually involves some coding. We're probably going out and querying a database, or in the case of the demo I'll show you, we're using Azure AI Index to pull in some information about the data scheme and the content. So there's a little bit more work involved than just prompt engineering. But the advantage of it is that, we don't, for example, we wouldn't have to go out and get the entire database and put it in the prompt, which it would never fit anyway. We would just want to put into the prompt the things that are very relevant to the single question at hand. And RAG helps us do that because we can just pick out just little tidbits that we need from some other system, put it in the prompt so that the LLM knows about it. So it makes a good decision about what to predict. I'll show you an example of this one as well. And I would say the effectiveness of RAG, quite high. You can get a lot of mileage out of using RAG because essentially you can plug all of the plug a lot of uncertainties in the what the LLM needs to do by putting it into the prompt and only put in what you need, not not overburden it. And then the final technique I'll mention is model fine-tuning. Model fine-tuning essentially is where you're taking an original model that perhaps Meta or Microsoft or OpenAI put together, and they train that model on an enormous amount of data. And model fine-tuning is a way to is to just modify a few layers of the original model with data that's specific to us. So this does have probably the highest effectiveness of any strategy because we can actually train the base model on our specific data, and that can be extremely powerful. But the effort is relatively high to do this because we need to use GPUs, and it is typically expensive. It takes a lot of expertise, but there are definitely cases where we can do this. We did some work with Q-LoRa tuning of a small language model for text-to-SQL, and it had a dramatic improvement on SQL generation. But I would just say about it is that it's the thing you do when you're trying to get the last little bit out of the models, and not necessarily the place to start. So if I was advising you, I'd say, well, you try RAG first. And if there are things that's just not quite doing, model fine-tuning probably makes sense. And model fine-tuning, as the state of the art is developing, we're seeing more and more is fine-tuning being applied to small models that are less expensive to operate. and fine-tuning those can actually result in better performance than RAG against frontier models like OpenAI, GPT-4, and so on. So anyway, but I'm not going to cover, I don't think I'm going to mention fine-tuning again. I just want you to know that, yep, it's there. And I'll show you a little bit of a pictograph to make that clear. But let me give you an example of each of these because I know these are complex words. It kind of probably makes sense, but let's give an example of these. So prompt engineering, and this is generally writing rules to put into the prompt that help the SQL generation, or if you're doing some other kind of LLM application like document summarization, you might do this as well. But for this presentation, we're really worried about text to SQL generation. And what we can do with prompt engineering is provide rules and instructions. So we might do things like these. So if we wanted to make sure that any SQL that's generated always had single quotes around the around literals, we could actually tell the LLM, just like this in plain language, that hey, all literal string values have to be single quotes. So that would prevent the LLM from using double quotes or not quoting literals, which it probably wouldn't do anyway. But this kind of instruction is kind of guiding it to generate the output that we want. Ensuring columns are delimited. In SQL Server, you delimit columns with the square brackets. And Snowflake, you delimit them with double quotes. So if you find that, well, the SQL that's coming out isn't, it's not delimiting things I want, or I want to make sure I have delimiters even if there aren't any spaces, this kind of prompt engineering, you tell the LLM, this is exactly what I want, and it will do it, generally speaking. And then the last one I've had to use where sometimes, especially GPT will, OpenAI GPT will give you the SQL as an answer, but then it'll like have paragraphs of information explaining why it did it the way it did it. And maybe we don't want that. So you can do things like this, but just say, hey, include the SQL. I don't want any explanation to go along with that because at the end of the day, you're paying for everything it generates by tokens. So just kind of like limiting it down. So it's prompt engineering. How does that look if you're actually writing a prompt? It would look something like this. So the red stuff is the prompt engineering. So the black stuff is, just the original prompt. So this is actually a complete prompt for text to SQL. It's not complete enough to generate a perfect SQL, but it would work. And here we say, you're an expert in creating SQL queries. We usually set this grounding so that we guide the LLM that, you're generating SQL here. So we don't want to see an essay about, the content. We want to see a SQL query. And then in the red, we said, hey, you can create SQL queries using tables defined in the table section. So here's a little bit of prompt engineering that we might do RAG sometimes on this, but here we're doing some prompt engineering to tell it what the table looks like. So if you remember the original example where it was guessing at the columns, a quick fix to that is give it the columns. So we say, hey, here's a table definition and just ANSI create table syntax, and that will tell it what the columns are. It's going to do a much better job in that case. And then I put in those other two examples, like all literal values are quoted with single quotes, and column names have to be, square brackets. And then we tell it now answer user question, by a SQL query that provides the answer as a SQL query. Oh, it's a little repetitive. Sorry about that. So then we state what the question is. So that's what the user entered in. We gave it the tables. So now we're going to limit the LLM to using just the table names that we gave it. And if there are multiple tables and join instructions, it could do that as well. And then the answer, we kind of leave that blank, and then the LLM is going to come back and give us SQL as a result of that. So it's kind of prompt engineering. Easiest thing you can do. You can get lots of miles with it. But it doesn't solve for things like users asking about content in the database that isn't part of the schema. So, for example, and this is where RAG can get into the solution. So, RAG is retrieval augmented generation. It's distinct from prompt engineering because usually with RAG, you're going out to some data source and pulling in some information that is relevant to the prompt, and then providing that to the LLM within the prompt. So in this case, it's a different query, but we might say how many derailleurs sold in 2008. So if we give this to an LLM, it will take a guess on what it's supposed to do. My experience with most big LLMs is they'll see 2008, they'll know that's a year. They'll try to find a column that has something to do with the year. It's probably going to get in the where clause where it's supposed to be. But that derailleurs, it's really not going to have any idea what to do with that. So you'll probably get a guess from an LLM on what that means. But we don't want guesses. We want deterministic, good SQL. So in this case, and this is an approach I've used, works really well. So you can like take the query first, send it to OpenAI model, and just ask it which words or terms it might be in a word clause. And it will actually return, well, derailers looks like that's going to be in the where clause. If it generates something, it'll give us derailers in 2008. And derailers is the one I'm worried about. I think it'll probably make the right decision about 2008. But what I want to know is what columns contain the text derailers in them. So in this sort of architecture, I've indexed the columns that are likely to be quoted in Azure AI Search. And so I can ask Azure AI Search which columns have the value derailers in them. And it returns that the most likely match is the category name. And I say, great. So now I can take the category name and give that to OpenAI and say, by the way, someone might ask about derailers. They probably mean category name. Make that assumption when you generate the keyword query. So this is different than prompt engineering because we're not going to put every value in every column in our entire database into the prompt because it won't fit. But we want to use Azure AI Search to sort of pre-process this. So we actually have two pre-processing steps. Those pre-processors are part of the retrieval. So we're retrieving what are the likely where clause terms, and then we're using those terms to find out what columns probably contain that, give that to OpenAI, and we get this query, which is actually correct because in this database, category name does contain derailers, and that's going to generate an accurate query. I have tried that. I'll try this during the demo, but during the demo, if you try this, it's going to say, well, derailers, maybe that's, I don't know, product description. Well, there's nothing in product description for derailers, so that wouldn't be a good query. So this approach is using RAG to sort of clean it up and get a better result in the end. So that's RAG. And then this is kind of an example of what that might actually look like. So this again, here's black is sort of the base prompt, and then the red is really the RAG part. So the base prompt is almost the same here. So it says, yep, you create SQL queries. You create SQL queries from text, from questions, and we have the table section down there. That's in this case we did that from prompt engineering, and then the red is where we said, hey, we're just telling the LLM there's this thing we called inferred columns. I made that up. It could be called anything, but it's just to kind of give it a place to look. And it said there's a section, it has a list of values of area of reference in the where clause. When one of these is found, assume it refers to the column indicated by the key inferred columns. So we gave it some JSON. And so what the LLM is going to do with this RAG generated content is it's going to find derailers, and then it's going to kind of back up to the key and say, well, that's category name. Yep, I'm going to select that from category name and then generate an appropriate query, which it actually does. And we'll look at that in demo. So that's RAG. Very, very powerful, very much. Always use RAG for almost anything that is dynamic and you need to reference large amounts of data. So the last technique I really wanted to talk about is model fine-tuning. And model fine-tuning is very important to know about, but I would call this an advanced technique. So this can be extremely powerful. And what we're doing with fine-tuning is, if you say this is GPT-4 or Llama 3, it's some large language model, and all these little dots represent parameters. So if you've kind of hear about a model has 7 billion parameters or it has 70 million parameters, those are sort of decision points that can be used to generate text. And when the model is when foundation model is pre-trained by whoever made it, so it could be Meta or Microsoft or OpenAI, they threw a lot of data at it and generated these kind of neural net parameters, if you will, and those are fixed for the moment, and we can influence how they're used a little bit with RAG or with prompt engineering, but we might want to go further with that. So and with many models we can. So what we can actually do is go into a fine-tuning process where we generate, thousands of queries from our database. Maybe we went in and captured the query log of what queries are actually being sent to our own database, and we can extract those and then use those to fine-tune the model so that, if you will, like on the right-hand side, you see those there's a few of those parameters out of, the 7 billion parameters. There's maybe a million that, we tweaked a little bit by training the model just on the very top, which is called LoRa. It's a like low rank adaptation. And we've retrained the model a little bit so that it becomes especially good at generating queries for our own database. So what this can do is actually minimize the amount of RAG or prompt engineering, because now the model's been modified so that when you give it sort of generic questions, it sort of defaults to our schema and defaults to the way we write queries. So this can be extremely powerful approach, but probably not where you start, but maybe where you end, in the process on the journey. So that's fine tuning. It's a very, very kind of a new field. Not a lot of people are doing it yet, but seeing it more. So are there any questions or any discussion that anyone would like to have before we kind of look at some of this in action? I don't see anything in the...
None have been posted to chat, but attendees are free to come off mute now if they would like to ask. Also at the end. Thanks.
Okay, well, I'll move on. If you do have any questions, let me know or come off mute. You're welcome to do that. So the solution architecture for the demo, I always kind of like to see when I see someone demo something, it's like, well, how's this thing really put together? So this slide is what I'm going to go through. I have a Streamlit web app. It doesn't have to be Streamlit. This could be React or Fabric Notebook or a mobile app. The point is that we have some kind of UI where we can ask questions. And this is just Streamlit because it's a really good prototyping tool that we use quite a bit. And so that Streamlit app is going to talk to an Azure Function app. And that Function app is really doing the marshaling between the backend services. So our core database that we're querying or asking questions about is in Azure SQL. And then I mentioned using RAG with Azure Search or Azure AI Search so that we could ask questions about database content. And then AI Search, we're leveraging in a RAG approach to take that content and then figure out, what columns is the user likely asking about so that we can hint OpenAI to generate a query that's specific to that part of the database. And then we're using OpenAI GPT-4o in this case to generate queries, also using it to ask it to parse out the questions to tell us, what's likely in the where clause here that we can do some RAG on. And we ask it a few other kind of preparatory questions like that. All this is behind a Azure Function app as a web service layer. It doesn't have to be. You could actually directly access these backend resources in Streamlit or in a web app or in a notebook. But this is kind of a design choice in this solution to put it into the Function app so that we're abstracting all of the heavy lifting away from the front end. And that allows us to have a web app that uses it, as well as a BI system that uses it, mobile apps that use it. So it's really kind of makes it pretty generic in that way. But anything in this case that can call a REST API could actually be a consumer of the solution that I'm going to go through. So that makes sense. So let me end this stop this sharing, and I'm going to share my screen so that I can go through some of this other stuff. So let me clean this up. Find the meeting again. There we go. Share. Now let's just share my own screen. That'd be easier. So the data source that we're going to query is this one. It's really tiny. I apologize for the font size, but if you're familiar with some of the AdventureWorks sample databases, this is one of those. So I created a view just to keep things simple that pulls together a lot of sales information. We have a lot to choose from, and we can ask about any of these in our solution. And the Streamlit app that I created to kind of play around with this is this one. So this is fairly straightforward. It's just kind of introduction to the assistant, telling us what it can do and inviting the user to do some things. I put in some sample prompts here. So as I demo, I'm going to choose a couple of these because it'll save me some typing, and you won't have to watch me make typing mistakes along the way. And then down here, I have the features I talked about where I can turn them on or off. So we can sort of try one of these prompts with having the table DDL in prompt engineering only, or we can add inferred columns where we're searching AI search for column values to pick the right column. So we can kind of play around with this a little bit and just see when we add these techniques, how much better does it get? What does it really look like? So that's kind of the setup here. So I'm going to start by giving the model nothing. So I'm just going to leverage the intrinsic text-to-SQL capabilities of GPT-4o, which if you use ChatGPT, that's kind of the same model. If you use Copilot, Microsoft Copilot, they use that model as well. They use GPT-4, sometimes 4o. So what I'm going to ask first is I'm just going to ask it to satisfy like what are sales by year, and just see what happens. So as I pick that, you see this top right corner, it'll say running. And what it's doing is it's taking that prompt and sending it out to Azure AI Services, which is then generating this SQL text. And it says select your sale date as year, sum sale amount is total sales from sales, group by sale. So it seems like really good query. The problem is that we got an error. It says, yeah, there's no such thing as the object name you're asking for. So it's kind of saying that there's no such table as sales. So not very helpful, definitely a fail. But let's try that again. And this time what we're going to do is we're going to do some prompt engineering, and I'm going to do that just by turning this on. So if you remember the slides where we could inject the DDL into the prompt. So that's what this checkbox is going to do. And let's just try that again and see if we get something closer to what we actually want. Okay, and this time I can see that it actually did work because I have a result set down here. So, this database only has 2008 in it, so that's why when it groups by year, there's only one. But I actually do get a result set this time. So it generated the SQL, and then the application turned around and ran that query against the database, and then I'll put it into tables here so we can see. So just by injecting the table DDL, we actually get something that's usable and much more helpful. So I'm just going to refresh the screen here. And this time we'll leave the DDL on, but let's kind of say, well, let's see how about that derailer example? How many derailers sold in 2008? And you see, we can get pretty detailed about our instructions here. So we want to sum by country, we want to order by the quantity sold in descending order. So let's go ahead and run that. And we're going to probably run into that problem with derailers. Will the model know what derailers means? And this time we didn't actually get an error, but there's no such product name as derailer. A derailer is a category of product, not a product itself. The 2008, it got that right. The quantity sold, it got right. Because it had the DDL, it actually used correct column names that got the schema right. So we're closer, but not quite there. So let's go ahead and now we'll put in derailer sold in 2008. And we're just going to turn all this stuff on now. And now, because we said derailers and we said add invert columns, this is going to make that transition through Azure A Search. So if you look at our diagram, so we're putting in the prompt, and the function now is going to have clearance to go ahead and ask AI Search, like, well, what columns have derailer in it? Return that to the function, and then it'll say, okay, great. Let's generate a query. So it'll go here next. Let's generate a query that uses derailers from the category. And then once it gets that back, it'll send it to the SQL database, and then it'll come back to the user. Hopefully that'll work. So let's try it. Running. Okay, and now we get something that actually works. So here it thought derailer must be a product name, or at least that's what its guess was. But with the RAG injection, now we're getting it selecting the correct column, which is category name for derailers. The rest of it is pretty much, I think that's the only decision it made that was differently. And United Kingdom keynote, that all looks pretty good. So that looks good. And then one other, I didn't mention in the slide, but one other sort of technique of RAG that we have in this solution is this one. So if we go up here and we say, you know what the DDL is, and here's what users will do to us, right? How many widgets sold in 2008? What's a widget? Sounds like maybe a product, right? So We know it's not because we're humans, so we know that's not really a product, but the product name equals widget. And that's not really what we're looking for. We have another sort of RAG approach in here where we have synonyms. So we have the idea that if this is essentially a map that we say if the user asks for zip, they actually mean customer postal code. And we're using this to hint the model as well. If they ask for sales, that really means line item total. If they say widget, because we noticed in our logs that people keep asking for widgets for some reason, really we're just going to map that to product number. So we're telling the LLM, if you hear this, that's kind of what they meant. And this, this list could go on for a long time, but let's try that one again. But this time we'll go ahead and allow synonym columns, which is what that feature does. And I didn't turn on inferred columns even this time, so just the synonyms. And now we actually get a better response. Now widgets maps to just product numbers, and it did determine that it didn't. The LLM sort of knew I don't need to use the product number to satisfy this query because they're just looking for like a total of products in the rest of the question. But the synonym at least let it know that that's not a where clause. They're referring to a column. It said, okay, that's fine. I don't need that. And it satisfied the rest of the query and came up with the right answer. And then there are just some different things in here. So we have, this one's a little more complicated. I didn't turn on my inferred columns though, so we'll see what happens. So we can get some fairly complex questions out of here. We can say, what is the standard deviation of sales and for turn on everything here for mountain bikes. See what it does. Didn't practice this one before the demo, so we'll all see together whether this works or not. Actually, that looks correct. So I've got standard deviation. Yeah, I mean, the syntax is right. I don't know if the number's right, but probably $3,000. Yeah, that's probably reasonable. So what's kind of gone on in the background is the base model sort of knows what to do with standard deviation. We told it was SQL Server, so it's actually choosing correct SQL Server syntax. And then the things that we're using RAG for is like knowing that mountain bikes is a category. It is not a description, it's a category. And getting all of these right. And when we said sales, we really meant line item total, so it got that right. Sometimes you'll find with an LLM, you won't need necessarily to hint it on everything. So if we just said sales, it might actually get line item total right, it might not. But the concept with using some of these techniques is that, as you're testing it and you find that, yeah, it's not quite getting this right or not quite getting that right, it's between prompt engineering, especially in RAG, you can really kind of tune it and dial it in to work exactly as you want to. So that's kind of the solution. I know this is not an extensive presentation, but I hope it gives you the concept of what we're trying to accomplish and some of the techniques you can use. For the most part, what we're doing here is using fairly generic concepts with LLM development and really fits into a lot of use cases and I hope it's useful and interesting. So, and did anyone have any questions? Got about 15 minutes on the clock, so
yeah.
Anybody's
Hi,
free to
Colin
unmute.
here.
Yep.
hey, Colin.
I'm curious about. I'm an AI newbie, kind of deliberately. I haven't been paying a lot of attention to it, but I assume every time you send a question to OpenAI, or let's just leave it at OpenAI, that's costing us somehow. When you expand a query or a prompt, sorry, to include RAG components, are you increasing the cost of the prompt that you're sending to OpenAI? How does the costing work out? And if that's a dumb question, feel free to correct me.
No, that's an excellent question. So essentially, when you're paying to run something on, or when you're paying to run an LLM model, you're basically paying for compute, more or less. So the way that, like, if we take Azure AI Services as an example, and you use their hosted OpenAI models like GPT-4o, which is what I'm using, the idea is that it gets charged per token. So the price might be this many cents per million tokens. A token is kind of, think of it like a syllable of a word. That's not what it is, but it's close. So to answer your question, yes, if I expand the prompt, let me find that. Let me find my PowerPoint here real quick. I think it's over here. So if we kind of go back to one of these prompt examples, so yes, putting in this section costs more than not putting it in, but it's like very tiny fractions of a penny. And you really kind of have to do it to get the result. Realistically, this is an extremely tiny prompt. Your prompt could be, I think the prompt windows, like several kilobytes or pages of prompt you could put in on the inbound side, without really putting a dent in it. But so for the like OpenAI services, the default model, the engine's running, it's in a shared tenant, and you're paying for prompt. It's a lot like any other service where you're paying for the bytes that you're putting in or out of a storage account or something like that. You can, though, set up your own compute and run your model on that. So you could actually provision VMs in Azure and install and use and deploy an instance of like Meta Llama 3 on there. And you wouldn't pay per the size of the prompt anymore, but you'd be paying for the GPU for like every second that it's running. So it's kind of like anything else. You can do a PaaS or SaaS. But yeah, the bigger the prompt is, the more the cost is. But you can actually estimate that. There are tools that OpenAI and others provide that you can, I could take this prompt and put it into a form, and it would tell me that's this many tokens. And then if I could say, well, I'll probably have 100,000 of these a day, and you can basically calculate out what that cost is going to be. Good question.
You've touched on an answer to my follow-up question, which was you talked about how you could either use like a default model, or you could do follow-up training on the model to look at your own data so that it automatically provides more meaningful answers for your use case. Is that a situation where you're basically going to run the model on your own hosted compute and not pay per token? Or is there a way to sort of augment OpenAI, I guess? What are you providing to OpenAI that might be your own proprietary IP that you're somehow getting them to execute for you? Clumsy question, but I hope you see where I'm going.
So are you more concerned with like fine-tuning the model or the sensitivity of the data that you're providing?
Yeah, good question. That was a confused. There's probably two questions there. One is, what's the best way to leverage training a model without leaking any potential dangerous or valuable IP? And the second question is, do you have to self-host it, for lack of a better term, in order to gain the advantages of a super trained model that's trained on your own stuff? You can punt on either of those questions.
No, I don't need to punt on either one. So this slide is the model fine tuning, which I think ties into your idea of like creating a model that's really your own, that knows your data intimately, and so you could actually train this on-prem if you wanted to, and then take the resulting it's called a LoRa adapter, and you could run that on-prem if you wanted to. So you don't have to do anything in the cloud. But if you if you do this in the cloud, which most people do, if you're using Microsoft Azure and you do it in a private VNet and you do it on, GPU compute that you deploy yourself, it's very contained. So I think you can probably satisfy most security, cyber requirements in that way. On the sort of PaaS version of the hosted models, Microsoft guarantees that your data is your data. They put it in writing that if you send data to OpenAI services on GPT models, that they won't use that data for training. They won't store it anywhere. It's kind of like most of their services. Not necessarily the case for OpenAI Direct. You've really got to read the fine print on that side, but Microsoft is pretty explicit about data privacy and so on. But if you were wanting to process data that was hypersensitive, you don't have to use cloud services to do this. You could do it on your own compute.
Got it. Thank you. I consider my questions answered. Thank you, Rob.
Okay, thank you.
Great. And Lisa is asking. Yep,
yeah, it's going to be really discombobulated. Sorry, Rob. And it's because the subject is natural language that I'm asking. So use the word derailleur. Let's say this is a Canadian French company and derailleur is the product type, but the English spelling is different for that word. I guess my question is, when a user asks natural language questions, is there a built-in something that queries the client for what the language coming in is, the way, browsers often do, or is where the large language model knows innately that it can look for synonyms in different languages for a string value, or is that something you have to build in as a translation table in your particular model and then tell it about it? Is this something that's, I'm sure it's a common problem. So the question is whether it's built in, I guess.
I mean, translation for the large frontier models like GPT-4o, they've been trained on many languages. So there's probably multiple ways to go about this in your case. And you might find that putting in some prompt engineering to say the following question is in French and I need you to find the answer in English, it would internally it would probably translate that and then satisfy the query. So the idea of like I guess the one idea I would give up on is like having translation tables, because with large language models it's more about like giving it the opportunity to predict the right answer without explicitly, doing that kind of a translation. So in your solution, I would probably first look for prompt engineering, detect what you could actually send a text to a GPT model and say, what language is this? And it's going to get it right like 99% of the time, if you wanted to do it that way. And then say, here's the question. The question is in French, query my database. There's probably a way to get there in that way.
So you're saying basically the question, it's some of one and some of the other. The ability to think about translation is built in, but OpenAI or whatever doesn't query the request for source language as a regular feature. You would tell it this question is in French.
Yeah, I mean, it wouldn't, because if you sort of think like your browser knows what the user's language is, but the large language model is probably not going to be seeing the user's browser. It's
no,
kind of
it's seeing a request, and some requests could have that built in as part of the API. So the question is whether or not that's an understood thing and that the APIs regularly add that as an attribute to the request.
You could. I'm not sure I'm following 100%, but if you're using the LLM to do the work, just doing prompt engineering to tell it that, analyze, here's the question, analyze what language it's in, then use that, translate that into English and look in the database, which is in English. It would actually probably do that pretty well. But, you could use, like you could add to the architecture to use, Azure AI translation instead and, translate it yourself and then ask. So there's just a lot of ways to go about it.
Okay.
But I would use an AI service to do the translation versus, a deterministic, table lookup approach, I guess is the way I would look at that first.
Okay. I mean, it just seems like we're in one world with one set of models. And it's probably, when you talk about natural language, it's probably one of the features that everybody would want. So I'm looking for how that is going to get more seamless. But I guess we're not there yet.
No, you'd have to dig in the details, but I think you'd find we might be more there, and I might not be understanding the question in its entirety. But I think you might find that we're not too bad, and that we could probably handle that kind of requirement with an LLM without augmenting it with too many other layers.
I guess as an analogy, if I have a self-driving car, I don't take it into a country where they drive on the other side of the road without inquiring whether it's built-in knowledge for that engine.
Mm-hmm.
And there would be two parts to that. One, it knows how to drive on both sides, and two, that it knows how to interrogate where it is such that it knows which of the two methods to use.
Yeah, I can definitely see that as being an issue. So,
Well,
so when you take that analogy and apply it to the natural language,
the first part is, how does it know what language the question was asked and does it need to be told? And the second is, once it knows, what are its resources for translation?
Okay, so the first part, I would say frontier LLMs is, yep.
So in your user interface, you can detect the code page the customer has in the client.
Right.
So that code page is the language. So now you identify what language the person is writing.
That's why I said it might be built into the request.
Yeah. And then you can translate whatever he's asking in English and then conform everything to English or vice versa, right?
Okay, thanks.
I think the ones I found challenging is when a database have different languages on the same field. Some rows in Japanese, some rows in Chinese, some rows in... Those are the ones that are difficult.
That would be in the realm of training on your particular model.
Yeah.
Okay, thank you, guys.